Okay, another Punnett square problem. Cystic fibrosis, a life-shortening disease, is regulated by a recessive allele C. So what that means is we have capital C is the normal case, no cystic fibrosis. Many people are this. Lowercase c is the allele for cystic fibrosis. So if you're big C, you are fine. If you are big C, little c, you are also fine. You are what we call a carrier for cystic fibrosis, but you don't have it yourself because the normal trait is dominant. So we have a little c saying that we should have cystic fibrosis and big C saying, no, we're not going to do that. And then there is little c, where there are two alleles for cystic fibrosis and nothing to stop them. And this is how you get a person who has CF. So they say, how could you have two normal parents who don't have CF, but they have a child who does? Here's what we know about our family tree. We have a mom who does not have cystic fibrosis. That means her genotype is big C, don't know. Right? If you're normal, you have one capital C, but we don't know what your second letter is, so we'd have to leave that empty. Over here we have a dad who is the same way. Capital C for normal, but don't know what this is. And their child has cystic fibrosis, little c, little c. How does that happen? Well, it's not too hard to work out once you have it laid out like this. Every time you have two alleles, one of these came from each of your parents. So if you have two little c's, mom gave you one of them. So she must have had that hiding. And dad gave you the other one, so you must have a little c there also. So two parents without cystic fibrosis can both be carriers for cystic fibrosis. And what that means is they have this allele for it even though they're not showing it themselves. And if mom's egg contains the recessive allele and dad's sperm cell also contains the recessive allele, then they combine and you get a person with the CF trait.